How does the Carnot cycle produce work? Imagine a perfect engine that can convert heat into motion without wasting any energy. That's what the Carnot cycle aims to do, but how exactly does it turn heat into work? Let's find out. The cycle uses a working gas that moves through four steps, all carefully designed to maximize efficiency. It operates between two temperature points, a hot source and a cold sink. The hot source gives off heat, and the cold sink absorbs some of it, but not all. The difference in heat flow is what creates work. First, the gas absorbs heat from the hot reservoir while expanding slowly at a constant temperature. This is called isothermal expansion. As the gas expands, it pushes a piston outward, doing work on the surroundings. The heat energy it takes in here is called Qin. Next, the gas continues to expand but now without exchanging heat. This is adiabatic expansion, which means it is insulated. During this process, the gas cools down from the high temperature to the lower temperature of the cold reservoir. The gas still does work during this step, but no heat enters or leaves. Then the gas is compressed at a constant low temperature, releasing heat to the cold reservoir. This is called isothermal compression. Work is done on the gas during this step, and the heat rejected is called Q out. Finally, the gas is compressed further without heat exchange, which raises its temperature back to the initial high level. This is adiabatic compression. No heat is transferred, but work is done on the gas, increasing its internal energy. Once this cycle completes, the gas returns to its starting point. The net work the engine produces is the difference between the heat absorbed from the hot source and the heat rejected to the cold sink. Mathematically, it is Q in minus Q out. This network is represented visually as the area inside the cycle on a pressure-volume diagram. The larger this area, the more work is produced. The Carnot cycle is special because it is an ideal model that shows the maximum efficiency any heat engine can reach between two temperatures. The efficiency depends only on the temperatures of the hot and cold reservoirs. It is calculated as 1 minus the ratio of the cold temperature to the hot temperature, both measured in Kelvin. This means that the closer the two temperatures are, the less efficient the cycle becomes. Understanding how the Carnot cycle produces work helps us see why real engines can never be perfect. It also explains why increasing the temperature difference between the hot and cold reservoirs improves efficiency. This cycle is a fundamental concept that guides how we design engines, refrigerators, and heat pumps. It shows us the limits of energy conversion and why we aim for the best possible efficiency in all thermal systems.